So I would like to now explore the next matrix operation with you, and that is the operation of matrix multiplication. So here we go. If A is an M by N matrix, and if B is an N by P matrix, then the product matrix A times matrix B is an M by P matrix such that the following holds true. So we have the product matrix A times matrix B. Now, we're going to leave matrix A as it is, but let's define matrix B in terms of its column vectors. So we can say that matrix B has column vectors B sub 1, we have column vector B sub 2, all the way up to a column vector B sub P. Now we can further rewrite this as a matrix whose column vectors are defined as matrix A times column vector B sub 1. Our next column vector is matrix A times column vector B sub 2. And this continues all the way to that last column vector defined as matrix A times vector B sub P. And this is where, again, all of these column vectors, so we have matrix A times vector B sub 1, matrix A times vector B sub 2, all the way up to matrix A times vector B sub P. These are the columns of this new matrix, or the columns of matrix A times B. So this is our formal definition for matrix multiplication. And there are a couple of important notes I'd like to make and observe with you here. So the first one is that this definition is showing us that for the product of matrices, matrix A times matrix B, that a matrix A can be written as a linear combination of the columns of matrix B. So we can see here, we can observe from the definition that matrix A can be written as a linear combination of the columns of matrix B. And I'll abbreviate the linear combo of the columns of matrix B. So did you observe that while we were looking at this definition? These columns should look familiar. So let's quickly recall, where do we know these from? Well, we know that if we have, say, matrix A times a vector X, and let's expand this out. Think about the matrix equation. So we can define matrix A as having column vectors A sub 1 all the way up to, say, column vector A sub n, multiplied by a vector in Rn. So the vector has n entries. So we know, of course, that the matrix equation is equivalent to the vector equation. So that's x sub 1 times vector A sub 1. Plus, we can even put in x sub 2 times vector A sub 2, plus all the way to x sub n times column vector A sub n. And this is the same exact thing that's happening in each one of these column vectors. We have a matrix times a vector. We have a matrix times a new vector. And this continues all the way to that last column where we have a matrix times a vector. So it's the same thing, just on a much larger scale. Now, the last thing I want to point out to you is the size of these matrices is very important to matrix multiplication, to the existence of that product. So from this definition, we can observe that the number of columns of the first matrix, the matrix A here, the number of columns of the first matrix must be equal to the number of rows of the second matrix. Otherwise, the product will not exist. So the number of columns in the first matrix must be equal to the number of rows of the second matrix. And we're observing that here with this definition. So let's make a little love note here to ourselves that in this definition we have matrix A defined as an M by N matrix. And we are also given this matrix B, and we are given that this is an N by P matrix. Now, before you start trying to take the product, you should always check. Do the number of columns of the first matrix match the number of rows of the second matrix? If they do, then you know that the product, matrix A times matrix B, exists. Now, what's also great about lining these two matrices up like this is that we can see the size of the new matrix. So we can not only check if the matrix or if the product of the two matrices exists, but we can also see that the product, matrix A times matrix B, is an M by P matrix. So again, this is an essential rule. The number of columns of the first matrix must be equal to the number of rows of the second matrix. If they're not equal, then matrix multiplication does not exist.